Sum operations with complex numbers. Part 1. Equality of complex numbers. Two complex numbers are only equal if they are equal in all respects, i.e. if the real parts are equal and the imaginary parts are equal. Equality of complex numbers. A plus bi is equal to c plus di if and only if for the real parts a is equal to c and for the imaginary parts b is equal to d. This definition of equality can be used to work out unknown coefficients in equations, sometimes by forming and solving simultaneous equations. Find the values of the real numbers x and y if 2x plus 3 plus x plus 1i is equal to 3y plus 4 plus 4 minus yi, where I squared is equal to minus 1. We are told that these two complex numbers are equal, so we put real equal to real and imaginary equal to imaginary. So 2x plus 3 is going to be equal to 3y plus 4. So 2x plus 3 is equal to 3y plus 4. They're the parts with no i's stuck on, so they're the real parts. And then x plus 1 is equal to 4 minus y. So x plus 1 is equal to 4 minus y. So they're the imaginary parts. So this is equation 1 and this is equation 2. Now we're going to solve these equations simultaneously. So equation 1, which was 2x plus 3 equals 3y plus 4, can be rearranged as 2x minus 3y equals 1. And x plus 1 equals 4 minus y, which was equation 2, can be rearranged as x plus y equals 3. Now we want to solve them simultaneously. So we're going to write out equation 1 again, 2x minus 3y equals 1, and we're going to multiply equation 2 by 3, giving us 3x plus 3y equals 9. Now we can cancel out the y's, and 2x plus 3x is 5x, and 1 plus 9 is 10. So 5x is 10, so 10 divided by 5 is 2, so x is equal to 2. And then subbing back into one of the equations, let's take the second one, x plus y equals 3. So x plus 2 equals 3 because we got x is equal to 2. And 3 take away 2 is 1, so y is equal to 1. Part 2, addition of complex numbers. Suppose z equals 2 minus 3i and w equals 1 plus 5i. Then z plus w is also a complex number which can be calculated by using the ordinary laws of algebra, i.e. adding the real parts and adding the imaginary parts separate. i.e. z plus w equals 2 minus 3i plus 1 plus 5i. Adding the real parts, we get 2 plus 1 equals 3. Adding the imaginary parts, we get minus 3 plus 5 gives us 2, so we have 2i. The addition of complex numbers on the Argand diagram is performed in an interesting way. If z equals 2 minus 3i, then z is represented by the point 2 minus 3 on the Argand diagram. So that's 2 minus 3, so there's the point z. The complex number w equals 1 plus 5i may be considered to be the translation from 0, 0 to 1, 5, i.e. a change of 1 in the real direction and a change of 5 in the imaginary direction. This translation may be written as OW with an arrow over it. Another word for this is a vector. Adding w to z may be interpreted as finding the image of z under the translation OW, i.e. z plus w equals z plus OW. From the diagram opposite, we can see that the image is 3, 2, which is equal to 3 plus 2i. So we have 3 plus 2i. So adding z and w, we get z plus w. If w equals 1 plus 5i is added to any other complex number, then that number will undergo the same translation. For example, if u equals minus 3 minus I, then u plus w is going to be minus 3 minus I plus 1 plus 5i. Adding the real parts, we have minus 3 plus 1 is minus 2. And adding the imaginary parts, we have minus 1 plus 5 is plus 4i. Which we can see from the diagram is the image of u under the translation OW. So this is the complex number u, this is the complex number w, and adding u and w together, you get u plus w. You should also note that w plus z may be interpreted as the image of the point w under the translation oz. From the diagram opposite, we can see that w plus z gives the same outcome as z plus w. So here we have z plus w, which is w plus z. So going from the origin up to w and then down by z, we end up at z plus w. Or going from the origin down to z and up to w, we still end at the same place. Part 2. The points O, W, z plus w and z are the vertices or corner of a parallelogram. So we have O, W, z plus w and z forming a parallelogram. The modulus of z plus w is not greater than the modulus of z plus the modulus of w, because one side of a triangle cannot be longer than the sum of the other two sides. So the modulus of z plus w is the distance from the origin to z plus w. So this cannot be longer than the modulus of z plus the modulus of w. Part 3. Negative of a complex number. If z equals 3 minus 4i, then minus z is going to be minus times 3 minus 4i, which will give us minus 3 plus 4i. So minus z is minus 3 plus 4i, i.e. both the real part and the imaginary parts are multiplied by minus 1. On an Argand diagram, if z is the translation oz, then minus z may be considered to be the translation minus oz, which is the same as the translation from z to o, i.e. minus oz is equal to zo. The translation zo is the same length as the translation oz, but the points are in the opposite direction. So from the origin out to minus z, we have minus oz, or you could call it zo. And from the origin out as far as z, we just have oz. Part 4. Subtraction of complex numbers. Suppose z equals 3 plus 2i and w equals 1 minus 3i, then z minus w is 3 plus 2i minus 1 minus 3i. Subtracting the real parts, we have 3 minus 1, which is 2. And subtracting the imaginary parts, we have 2 minus minus 3, which is 2 plus 3, which is 5. i.e. subtract the real parts and subtract the imaginary parts separately. On an Argand diagram, z minus w means that we start with the point z and translate it by the translation minus ow, which is the same thing as wo, i.e. move z the same distance but in the exact opposite direction to ow. So if ow is going from the origin to w, then minus ow is going from the origin out to here. So z minus w, if this is the point z, 2, 3, then z minus w, we end up here, the point 2, 5. Part 5. Multiplication of a complex number by a real number. The complex number z equals 8 plus 6i can be represented by the point 8, 6 on an Argand diagram. And the modulus of z is equal to the square root of 8 squared plus 6 squared, which is the square root of 100, which is 10. Below are some examples of what we get when we multiply z by a real number, k. And k must be an element of the real number set. So 2z is going to be 2 times 8 plus 6i, which is 16 plus 12i. So i.e. multiply both the real part and the imaginary part of the complex number by 2. On an Argand diagram, 2z is represented by the point 16, 12. And the modulus of 2z is the square root of 16 squared plus 12 squared, which is root 400, which is 20. So we see here we have z, and here we have the point 2z. Thus, the modulus of 2z is twice that of z. And so 2z is twice as far from the origin as z. So we can see this is the origin, and this is as far up as z. and the distance from the origin to 2z is twice that of z. The translation to OZ is in the same direction as the translation OZ, but is twice as long. In this sense, multiplying a complex number by 2 can be considered as an enlargement or stretching of the complex number by a factor of 2. Now let's look at a half times z, which is going to be a half times 8 plus 6i, which gives us 4 plus 3i, i.e. we multiply both the real part and the imaginary part of the complex number by a half. On an Argand diagram, a half z is represented by the point 4, 3. So there we have a half z. Remember, this is z and this is a half z. And the modulus of a half z is the square root of 4 squared plus 3 squared, which is root 25, which is 5. Thus, the modulus of a half z is half that of z, because 5 is half of 10. And so it is half as far from the origin as z. So the distance from the origin to a half z is half the distance of the distance from the origin to z. The translation a half OZ is in the same direction as the translation OZ, but is half as long. Hence, multiplying a complex number by a half can be considered a reduction or a contraction of the complex number by a factor of 2. Now let's have a look at minus 2z. So minus 2z is minus 2 times 8 plus 6i, which is minus 16 minus 12i, i.e. multiply both the real part and the imaginary part of the complex number by minus 2. On an Argand diagram, minus 2z is represented by the point minus 16 minus 12. So here we have the point minus 2z. So notice that this is the origin and this is positive 2z. So they're in the same place, just on the opposite side of the origin. So the modulus of minus 2z is going to be root minus 16 squared plus minus 12 squared, which is root 400, which is 20. As the modulus of minus 2z is equal to 2 times the modulus of z, minus 2z is twice as far from the origin as z. The translation minus 2oz is in the opposite direction to the translation of OZ and is twice as long. Z equals 4 plus 5i and W equals minus 3 plus 2i, where I squared is equal to minus 1. Part 1. Calculate 3z minus 2w in the form of a plus b, I. So 3z is going to be 3 times 4 plus 5i, because z is 4 plus 5i. And minus 2w is going to be minus 2 times minus 3 plus 2i, because w is minus 3 plus 2i. So once we've set this up, it's just a case of multiplying out the brackets and simplifying, putting the real parts with the real parts, the imaginary parts with the imaginary parts. So 3 times 4 is 12, 3 times 5i is 15i, minus 2 times 3 is 6, minus 2 times plus 2i is minus 4i. Next we put the real parts together. 12 plus 6 gives me 18. And 15i minus 4i, so 15i minus 4i, give me 11i. So the answer is 18 plus 11i. Make sure the real part comes first. Part 2. Show that the modulus of z plus 2w is less than the modulus of z plus twice the modulus of w. So the modulus of z, so z is 4 plus 5i, so the modulus of that will be the square root of 4 squared plus 5 squared, which gives us root 41. And then the modulus of w, well, w was minus 3 plus 2i, so the modulus of minus 3 plus 2i will be the square root of minus 3 squared plus 2 squared, which is root 13. So this formula is the square root of a squared plus b squared, where the a is the real part and the b is the imaginary part, but without the I. And this comes from Pythagoras' theorem. So if you want to understand where this formula actually comes from, look at the previous video. So the right hand side is the modulus of z plus 2 times the modulus of w. So the modulus of z we got to be root 41. The modulus of w we got to be root 13. So that's going to be 2 times 13. And then adding, we get approximately 13.61. Now the left hand side is the modulus of z plus 2w. So z is 4 plus 5i. w is minus 3 plus 2i, and we have a 2 stuck in front because we have to multiply it by 2. So we're going to work out what's inside the modulus symbol and then apply the modulus formula. So 4 plus 2 times minus 3, which is minus 6, so 4 minus 6 is minus 2. And then 5 plus 2 times 2, which is 4, so 5 plus 4 is 9i. So now we have our complex number. Now we apply the modulus formula. So the a is the minus 2, that's the real part, minus 2 squared. And the 9 is the b, that's the imaginary part, 9 squared. And we get root 85, which rounds off to 9.22. So as 9.22 is less than 13.61, the modulus of z plus 2w is less than the modulus of z plus 2 times the modulus of w. So we have shown that this is true. The Argand diagram opposite shows the 6 complex numbers a, b, c, d, e and f. So a, b, c, d, e and f. If these points represent the complex numbers z, w, 2w, minus z, z plus w and z plus 3w, identify which points represent each complex number. By copying the diagram, explain your reasoning. So as the translation from O to B is twice the translation from O to C, we can say that C is equal to W and B is equal to 2W. So let's look at the translation from O to B. So O is the origin and B is this point out here. And from O to C, O is the origin and C is this point here. So we can clearly see that from O to B is twice the length of from O to C. And so since in our options that were given, we have a W and then we have a 2W, the W must be C and the 2W must be B, because this is clearly twice this. As the translation O to A is equal in length but opposite in direction to the translation of O to F, one of these points is Z and the other is minus Z. So from O to A and from O to F, we can see that they are the exact same distance from the origin. They're just going in opposite directions. So one of them must be Z and the other must be minus Z. As OCEF is a parallelogram, so OCEF is a parallelogram, F must be Z, giving E as Z plus W. So F must be Z because we have another option which is Z plus W. Because we've already said that C is W, so F is clearly going up in the same direction as C and by the same distance. So E must be Z plus W. Z plus W. Also, A is equal to minus Z. Well, if we've decided that F of Z is Z, then A must be minus Z. Thus, F is equal to Z, A is equal to minus Z, and E is equal to Z plus W. Finally, D must be Z plus 3W. So D is equal to Z plus 3W. Obviously, that's the only one that's left, but we can also confirm it by drawing a line from F to D and breaking it into 3 parts. So if from O to C is W, then from F to E is 1, 2, 3 W's. So we've got Z plus 3W. Part 6, multiplication of a complex number by a complex number. To multiply one complex number by another, we multiply using the ordinary laws of algebra. Just think of I as a letter just like X, except that whenever we meet I squared, we replace it by minus 1. Part 1. If Z is equal to 1 minus 5i and W is equal to 1 plus 2i, express Z multiplied by W in the form of A plus BI. So Z times W is going to be 1 minus 5i times 1 plus 2i. So this is just binomial expansion. So we crack open the first egg, we bring down the 1, we stick on the second egg or the second set of brackets, we bring down the minus 5i, and again we stick on the second egg or the second set of brackets. We multiply out our brackets and we get 1 plus 2i minus 5i minus 10i squared. 10i squared becomes minus 1. Very, very important that you must have brackets around this because we're going to have to multiply minus 10 by minus 1, which gives us positive 10. I'm putting the real parts together. 1 plus 10 is 11, and just bring down the minus 3i. So you get 11 minus 3i. Make sure the real part comes first. Part 2, if u equals k minus 5i and v equals 1 plus 2i, find the value of k, which is an element of the real number set, for which u multiplied by v lies on the imaginary axis. So u multiplied by v will be k minus 5i multiplied by 1 plus 2i. So again, we crack open the egg, we bring down the k, we stick on the second set of brackets, 1 plus 2i, bring down the minus 5i, stick on the second set of brackets again. Multiplying out, we get k plus 2ki minus 5i minus 10i squared. Again, the I squared becomes minus 1, and again, make sure you've got brackets around it because we have to multiply. Here we're going to factorize. We're going to take out the I, which is common to both, and we're going to have 2k minus 5 in brackets. And then minus 10 by minus 1 is plus 10. Next, we put the real parts together. So basically anything without an I. So k plus 10 is the real part. And then 2k minus 5 is the imaginary part. If this complex number lies on the imaginary axis, then its real parts must be 0. So if this is our real axis, this is our imaginary axis, and our point lies on the imaginary axis, it doesn't matter where it is, let's say it's here, then it must have a real value of 0. So we take the real parts, which is k plus 10, and we let them equal to 0, and then we solve for k. So k is equal to minus 10. The interpretation of the multiplication of complex numbers on an Argand diagram will be studied in detail later. For the moment, we will just state the following result. Suppose the angles that z and w make with the positive sense of the real axis are alpha and beta respectively. Then the angle that z times w makes with the positive sense of the real axis is alpha plus beta, i.e. we add the angles. Also, if the lengths of z and w are the modulus of z and the modulus of w respectively, then the length of z times w is given by z times w, the modulus of that, is equal to the modulus of z multiplied by the modulus of w, i.e. we multiply the lengths or the moduli. So the angles that z and w make with the positive sense or the positive side of the real axis, so this is the positive part of the real axis, so the modulus of z is alpha and the modulus of w is beta. Then to get z plus w, we add the two angles together to get alpha plus beta. And if we're interested in modulus, then the modulus of z, the distance from the origin to z, and the modulus of w, the distance from the origin to w, the length or the distance. We multiply these lengths to get the modulus of z multiplied by w.